So electrons are present in atoms, and that led to a lot of other questions. Well, if there's negative electrons inside these atoms and the atoms are neutral, there must be something positive in there to balance the charge. What are those positively charged things, and how are these little particles arranged? Is it a jumble? Are there more particles? Are they solid spheres? What are they? So Thomson came up with what's known as the plum pudding model. In the United States, we don't eat plum pudding. That's a British dessert. Think of a blueberry muffin. So blueberry muffin, you've got the muffin part, and then you've got blueberries, and they're just kind of randomly distributed. And this was Thomson's model for the atom. Now, it's silly now, we know that, but you have to start somewhere, right? So the plum pudding model said, well, here are the electrons, and they are like the blueberries in this muffin. And the muffin part is this positive charge. So there's this sphere of positive charge, and then we've got these negatively charged electrons, and they're just sort of randomly distributed in there. So this is something then that could be tested. So they tested it. Before we get into that, we do have to talk very briefly about radioactivity. And this came up just a minute ago. So radioactivity is the emission of small energetic particles from the core of certain unstable nuclei. And this was actually discovered in the late 1800s by Henri Becquerel and Marie Curie. As a result of this discovery, this allowed scientists to probe the structure of atoms. There are three basic types of, there's actually a fourth one. There's alpha particles, beta particles, and gamma rays. Alpha particles are the most positively charged and the most massive of the particles. We'll talk more about radioactivity in chapter 20, which would be covered in Chem 1B. So Rutherford was a student of Thomson's, and he set out to test this plum pudding model, and he was trying to prove that it was correct. So he did an experiment where he took positively charged alpha particles and directed them at a very, very thin sheet of gold foil. Now, the plum pudding model would predict that those particles would go straight through the gold foil because it's just a region of positive charge with these little tiny electrons in it. So here's an illustration of the setup. Here's a source of alpha particles. So we've got this beam of alpha particles that we're shooting at this very thin piece of gold foil. What happened was most of the particles went through with very little deflection, if any, but some of them basically bounced back. This was shocking. This is not what they expected to happen. Rutherford said this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A 15-inch shell from a gun, what kind of gun would that be? Cannon, maybe? 15 inches, right? That would have to be like a cannonball, right? So 15-inch cannonball, and you're shooting this at a piece of tissue paper, and it bounces back and hits you in the face. Aside from being dead, you'd be really surprised, right? This is crazy. So what was going on? Well, obviously the plum pudding model was not correct. So they had to come up with something else. Plum pudding model says that those particles should just go straight through. So the conclusion drawn from this experiment was that the matter must not be as uniform as it appears. There must be something that's very, very dense for these particles to hit. Most of them went through, but about 1 in 2,000 came back. They hit something massive enough that they bounced off. So the idea was that that's the nucleus. And if the alpha particle struck the nucleus, it would bounce back. If it went to the side of the nucleus, it would go straight through. So this theory explained the results of the experiment. So inside this nucleus are the protons. Question?
So when it collides with the nucleus, does it cause any change in the nucleus, or
That's a good question. When the alpha particle collides with the nucleus, does it cause any change? In this instance, it did not. You can initiate change by bombarding something with alpha particles. But I think nothing really happened here because gold has a very large nucleus, and so the little alpha particle is just like hitting a brick wall, just bouncing off. So inside the nucleus are the protons and the neutrons, and the electrons, those little teeny tiny things, are out here somewhere. So this led to the nuclear theory of the atom. The ideas here, most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space, and in that empty space are the tiny negatively charged electrons. There are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus, so the atom is electrically neutral. So this model was really successful, but they did realize that it wasn't quite complete. And an example of how it didn't quite work out was that a hydrogen atom contains one proton, a helium atom contains two protons, but the mass of helium is 4 times larger than hydrogen, not 2 times larger. So there must be something missing in here. Rutherford and one of his students, Chadwick, later determined that unaccounted for mass was due to neutrons, neutral particles inside the nucleus. So the neutrons have no electrical charge, they're neutral. So neutral and neutron both start with NEU, new. Neutron, neutral. Well, actually, they're both NEUTR. The mass of a neutron is very similar to the mass of a proton. And so they could explain this relationship between the masses of hydrogen and helium because a hydrogen atom has 1 proton in its nucleus and no neutrons. The helium atom has 2 protons, but it also has 2 neutrons. And so its mass is 4 times larger than a hydrogen atom. The electrons are so small that the number of electrons doesn't really matter in terms of the mass. So the structure of the atom. We've got the nucleus. It's extremely dense. It's very small. It occupies very little space in the atom, but it has more than 99.9% of the mass. If you were able to take just nuclei and get enough of that together to make a dot the size of a period in your book, it would weigh millions of tons if you just had nuclei. Of course, you can't do that. The book uses a cloud analogy. So the electrons are like water droplets in a cloud. They don't have significant mass, but they're spread out, and the cloud is occupying a large volume, right? And yet the cloud is mostly empty space. You can walk through a cloud. Here is, we're very familiar with fog, right? Fog is essentially a cloud that's just down here on the ground with us. So fog, right? Little tiny droplets of water. They obscure vision. We can't see through the fog, but you can walk through the fog very easily, right? Because the particles are really small. The fog is mostly empty space. Matter is mostly empty space. it seems solid because the variations are too small for our eyes to detect. So if we think about some scaffolding the size of a football field, 100 stories tall, right? Can you imagine that? Like a big jungle gym that you could climb on. It's mostly empty space. But if you back up far enough, like an airplane flying thousands of feet above, and looking down on that, it would look like a solid object. Because being that far away, you're not able to distinguish the difference between the bars and the spaces in between. They sort of blur together. That football field analogy, if the atom was the size of a football field, the nucleus would be the size of a green pea. So imagine that, football field, and you've got one little pea on the 50-yard line. All the mass is in that little pea, and the rest, this sphere, as long as the football field, is empty. Matter's empty space. And yet, you punch the desk and you're going to hurt your hand, right? How does that work then? Well, this is like, if you rap on the desk with your knuckles, that's like taking one giant scaffolding and banging it on another one, right? They're both mostly empty space, and yet they don't fall into each other. Any questions? You can see how that could lead to a lot of, science fiction type plots. It's just like, well, we could do all sorts of things with this. I mean, why not take the particles of someone's body and transport them somewhere else and reassemble them? Why not shrink matter or make it much larger, right? Have a lot of fun with that.